And welcome back. In section 1.5, we go over the properties of real numbers. And properties in general are going to be a big topic in this course. Alright, so we'll start with the order property of real numbers. So if A and B are elements of the set of real numbers, and in section 1.4 we went over in detail what that entails. So A and B are in the set of reals. So they could be natural numbers, they might be irrational numbers, they might be integers, they might fall into several categories at once within the reals. We went over some of that in 1.4. So A and B are in the reals, and A is less than B. Then A is to the left of B on the real number line. Now some other inequality symbols aside from the less than. A less than or equal to B means either A is less than B, or, and remember we're using the inclusive or, A is equal to B. So if it's this category or this category, this would be a true statement. And we can kind of make these similar definitions if we have greater than or equal to. If A is greater than B, A is to the right of B on the real number line. So you can construct similar definitions for the other two inequality symbols. Okay, so equal, not equal to, greater than, less than, greater than or equal to, less than or equal to. So we'll make a couple of comparisons. So for example, a -5 with a +4, I'll just insert. Since -5 is to the left of +4 on the real number line, we can use a less than. That means we can also use a less than or equal to. They're clearly not the same number, so I can also use a not equal to. If we have, let's say, -9 and -15. Okay, so this is one that will kind of catch you if you're not paying close enough attention. Remember how the number line is constructed. We've got the 0 over here, 1, 2, etc. going that way. -1, -2, we will run into the -9 before we run into the -15. So -15 is on the left. That means that is the smaller number, so this would have a greater than or equal to, and of course we can also use a not equal to. 16/8 and square root of 4, we may have a little bit of simplifying to do. So 16/8 is worth 2, root 4 is also worth 2. So there's actually 3 symbols that we can use for this. See if you can figure out which 3 symbols it is, and go ahead and pause it if you need to. Okay, so our 3 symbols, of course, we can say that they are in fact equal. Less than or equal to would still be true because we have the or equals part of that statement. Similarly, we could use a greater than or equal to symbol and still create a true statement between the 2 values. Okay, again, we're going to define our working environment here. We're going to let A be in the set of real numbers. Absolute value is another idea. Absolute value of A denoted with the vertical bars is the distance between 0 and A on the number line. Now, distance is a non-negative concept. You're just talking about how far apart it is. You don't care what direction it is. So for that in symbols, we can say absolute value of A is at least 0. So notice nothing else is going on outside of the absolute values on this left-hand side of this statement. Just have an absolute value by itself, and we can say with confidence that that is at least 0. If anything else is happening outside of the absolute value, I can't make that guarantee anymore. So the absolute value of -17, that would be 17 units from 0. Absolute value of 6 is still 6. We're 6 units away from 0. So next we look at a few axioms. These are properties that we accept as being true. So for this one, we're going to let A, B, and C all be elements of the set of real numbers. Associative property that appears in both addition and multiplication. Associative property of addition. You have 3 numbers and you're finding a total. You can group either pair together. The first 2 or the last 2 together, you'll get the same result every time. If we're talking associative property of multiplication, similar idea, just with multiplication. AB times C is worth A times the product of B and C. We have the commutative property. So commutative property of addition. A plus B is the same as B plus A. We can move the terms around. Of multiplication, we can move the factors around. Another property, distributive property, or if you want the full name, of multiplication over addition. A times quantity B plus C has the same results as AB plus AC. A little hint on future sections of this, and even one or two problems in this. This is not a one-way street. Distributive property either starts us here or and ends here, or sometimes it'll start in this form and we will work it back to this form. That is still the distributive property. So even if we see it in the other order, that is still under the distributive property. So it's not a one-way street. Equal sign means has the same value, is the same as. So I'm going to have you try to identify the property used. And I'll put a handful of them up here. We'll start with these three and then do the next three in a moment. So go ahead and pause it, try to name the properties. Okay, welcome back. So this first one, we had two factors and they changed order. The 8 was first, then the 8 was second. We were moving things around, we are commuting. So this is the commutative property specifically of multiplication. Next one, 5 times 7 times 2 turned into 7 times 5 times 2. The same thing happened. The order of these moved around. We just happen to have another factor. So this is also the commutative property of multiplication. The third one, everything was written, all the numbers were written in the same order. The 8, then the 7, then the 19, 8, then 7, then 19. Our grouping just changed. First two together, last two together. That tells us we're working with an associative property. And this was an addition problem, so associative property of addition. All right, so our next view, we'll continue that on the next page. Same instructions. I'm just going to give you a few new problems. So 5 by the quantity 6 plus 8 is worth 5 by 6 plus 5 by 8. 9 plus 2, quantity plus 3 is worth 3 plus the quantity 9 plus 2. And finally, 9 times 7 plus 9 times 5 is equal to 9 times the quantity 7 plus 5. So see if you can name all three of those properties. Pause it if you need to. Okay, welcome back. So this top one, we had a multiplication problem over an addition. That is the distributive property. We rewrote a product as a sum. This one, the 9 plus 2 were grouped together and they were at the front of the line. Now they're at the back of the line, but it's still the 9 and 2 grouped together. So this is the commutative property of addition. And the last one, hopefully you recognize as still being the distributive property, just working sort of quote unquote backwards from how we did before, but it's still the same property. All right. Now, one thing I want to do is prove that subtraction is not associative. Now, to prove something does not have a certain property, all you need is one counterexample. So show me one case where it doesn't work, and you've proven to me it does not have that property. So, for example, I can say, all right, well, is 12 minus 2 in parentheses minus 5, is that the same as 12 minus the quantity 2 minus 5? If it is, it might be associative, but it's not enough to prove that it is associative. But if it doesn't work, it is enough to show that subtraction is not an associative operation. So our left-hand side, grouping symbols first, and we'll do a little more work more formally with order of operations in a minute. So 10 minus 5 is 5. I'll keep the question marks since we don't know if they have the same value. I'm not just going to state that they are equal. And 12 minus a negative 3 is worth 15. Definitely not equal, so that's enough to show that subtraction is not associative. So just one counterexample is all that it takes. Some more properties. Identity element. The identity element of addition, it's something that anytime you add this number, your answer is the same as what you started with. Of course, that is 0. Any number plus 0 is the same as 0 plus that number is worth that number, whatever A was, any A in R. Multiplication also has an identity element. And you guessed it, hopefully, 1. A times 1 is worth the same as 1 times A, which is just worth A. So there are different identity elements depending on what it is that you're working with operation-wise. So next up, we take a peek at the idea of inverses. Two numbers are inverses of one another under an operation. When they form the identity element for that operation. So for example, 7 plus a negative 7 is worth 0. 0 is the additive identity, so that tells me that 7 and negative 7 are what's called additive inverses. Similarly, negative 19 times negative 1/19 is worth just a plain boring positive 1. Negative by negative is a positive, and the 19's drop. So negative 19, negative 1/19 are multiplicative inverses of one another. And in general, for any a in the set of real numbers, a and the opposite of a are additive inverses. So just flip that sign. If b is in the real numbers and not worth 0, b and 1 over b are multiplicative inverses. Okay, so see if you can find the additive inverse and the multiplicative inverse of negative 2/3 and of positive 16. So pause it if you need to. See if you can find those four numbers. So additive inverse, opposite of negative 2/3 is positive 2/3, and if you add these two together, you get 0. Multiplicative inverse, reciprocal. We want to be able to multiply to a positive 1, so that means the sign is still going to be the same, and we flip the fraction. So negative by negative is a positive, 3's drop, 2's drop, and we get a 1 as our product. Additive inverse, the opposite of positive 16, negative 16. And multiplicative inverse, if you multiply 16 by 1 over 16, you'll get a product of positive 1, the multiplicative identity element. Okay, so from previous courses, hopefully you also remember that there is a way to expand some of these properties to problems that involve subtraction or division. So a minus b, hopefully you recall from your Math 93, Math 95 days, or the equivalent somewhere else, is the same as a plus the opposite of b. And for b non-zero, a divided by b can be rewritten as a times the reciprocal of b. So then we can, once we've turned them into addition or multiplication, then we can apply any of the properties that we want as far as moving things around. So if I had negative 13 minus 19 and I wanted to use the commutative property, first I would have to rewrite it as negative 13 plus a negative 19, and then I can go ahead and swap them, so then that would be negative 19 plus a negative 13. So it is still possible to use the commutative property. We just have to take one step and rewrite it as adding or multiplying instead of subtracting or dividing. One other thing, property of real numbers that hopefully you remember from all your previous math coursework: division by 0 is undefined. And for that one, I can kind of show you an example of why that would be undefined. So we'll just do just a basic integer division problem. Now there is an equivalent multiplication problem. So this symbol just means there's an equivalent statement that we can make. That would be that 4 times 3 gives us the result of 12. So any division problem has an equivalent multiplication problem. Well, if I took, we'll just stick with 12 for now, and divided by 0 and claim that it was worth some number, then I would have to claim that, let's see, where the 4 was, we have an n. Where the 3 was, we have a 0. That some number times 0 is worth 12. Hopefully you recognize that that is a contradiction. Any number times 0 is automatically 0. N times 0 cannot be 12. So there is no number that will get this job done. So 12 divided by 0, we would just say undefined. And I did mention we were going to do a quick little mini review of the order of operations to simplify an expression. And that's a 4-step process. So the first thing we look for are operations within grouping symbols. So those can include parentheses. So here star is just some operation. Could be addition, could be division, some mathematical operation. Brackets are sometimes used as well. They're more often used when there's more than one set of grouping symbols in the same problem. Braces, like we saw in our set days, and again for the same reason, if we have several sets of what they call nested, one inside of the other grouping symbols. Those are the ones that most folks remember. Some folks do forget if we have an operation underneath a radical. Even though they don't write them down for us, we picture it as having a set of parentheses around there until we have one number parked underneath that radical. Same thing within an absolute value. Keep working until you have one number inside that absolute value. And same thing with fraction bars. Fraction bars count as division. We're assuming that C star D is non-zero. Even though they won't write it down for us, we're picturing them grouped together. And here we have sort of two separate sets of grouping symbols. We work until we have one number for the top, one number for the bottom. And then we check to see if we can do any more simplifying after that. We move on to the next step. So grouping symbols. Then we have radicals and exponents. After that, division or multiplication. And if we have multiple instances, always left to right, assuming that we've taken care of the grouping symbols already. Grouping symbols are the only thing that can change the order of that and have us simplify something on the right before something on the left. And then we finish it off with subtraction or addition. Also left to right. All right, so let's try 8 minus 3 cubed minus 4 plus 6 squared divided by 9 times 2 minus 4 squared. And of course, since you want the credit for the problem, you're going to do them one step at a time instead of just keying it all in and writing one number down at the end, that's not really worth any points. So grouping symbols, I do see one grouping symbol, so I'll change that one thing. Everything else gets brought along as it was. So that's another important thing. The problem can't simply have parts of it that just up and disappear for a while and then reappear later. I did still write this in parentheses, but I don't have any more operations inside of those parentheses, so these are no longer grouping symbols, and I don't see any other grouping symbols. So then I look for exponents and radicals, and I see plenty of those, so let's take care of those. So 5 cubed, 5 times 5 is 25, times another 5 is 125. The minus 4 has to wait its turn, so I bring it along. 6 squared, though, I can replace that with a 36. Divided by 9 times 2 minus, and then 4 squared is worth 16. So we took care of any exponents and radicals on step 2. Multiplication division from left to right. So sometimes you multiply first, sometimes you divide first. It depends on who we run into first, left, or right. This time it happens to be division first. So 36/9 is 4. We still have more multiplying and dividing, so again, everything else comes along, and we take care of any remaining multiplying and dividing. And then we're finishing it off, addition, subtraction from left to right. Here we'll do subtraction, then addition, then subtraction again. So $1.25 minus 4, 121, and hang on to the plus 8 and the minus 16. 121 plus 8, 129, which I'll write as 129 this time, minus 16. And then we have just one last operation. So 113 is our end result. And again, if you want the points, you want to fill in this middle part. Let's walk through another one. Let's see, we'll do 2 to the 5th minus square root of 121 times 8 minus negative 16 plus 2 over negative 3 minus a negative 4. Okay, so this one, I see 2 sets of grouping symbols. So they didn't write them down for me, but I have an operation in the numerator